To the One World Combinatorics on Words seminar. Our speaker today is Markus Whiteland from the University of Liège, and he is going to tell us what he knows about Parikh-collinear morphisms.
Thank you, Narad. Thanks everyone for joining. Indeed, this is what I plan to tell you, and this is based on joint work with Michel Rigaud and Manon Stipulanti at the University of Liège. So let me just start by introducing the main notion. So just for some notation, we have the usual number of occurrences of a letter appearing in a word denoted with this absolute value with the subscript A. And C of W is the Parikh vector of a word. So now a Parikh-collinear morphism is you take a morphism from the alphabet A to B star, and we call it Parikh-collinear if for any pair of letters A and B, the Parikh vectors of the images of these letters are linearly dependent. So essentially, the Parikh vectors will span a 1D subspace. As an example, just consider the morphism 0 goes to 3 zeros and 3 ones, and 1 goes to 0, 1, 1, 0. This is Parikh-collinear because, well, the Parikh vectors are multiples of each other. Other examples, maybe the most well-known is the to-a-morse morphism, of course, and just another morphism here is just to illustrate that we allow here erasing morphisms. So you have that 0 and 1, their images have the same Parikh vector, but 2 has the all zeros Parikh vector. So in the literature, we can find Parikh-collinear morphisms discussed in passing. So for example, in works of Decking, Alouche, Decking, and Kefelet, and Cassain, and others. Let me just mention an interesting result that we will be developing through this talk. And for that, I'm going to need to introduce some further notation. So factor complexity function of an infinite word. We all hopefully know what it is, but just as a reminder, you have your fixed infinite word x, and for each n, you count the number of factors of length n appearing in your infinite word, and this will give you the factor complexity function. And while you can start now relaxing this counting. Sorry?
You maybe play it out loud, it doesn't bother me at all.
Sorry, I can't hear the question properly. Yeah, so
sorry, go ahead, Markus.
Okay. Yeah, so please feel free to interrupt if you have anything to ask. I forgot to say. So yeah, we're going to consider some complexity function where we relax this counting. So we're only going to count factors if they're sufficiently different enough. So here's one example coming from the abelian equivalence relation. So you have two words that are abelian equivalent if they have the same, two finite words are abelian equivalent if the Parikh vectors are equal. And from this, you can define the abelian complexity function. So here now instead of counting all factors of length n, you're going to count the number of abelian equivalence classes you see among factors of length n. And how is this related to Parikh-collinear morphisms? Well, this is a result of Cassain, Richaume, Sari, and Zamboni saying that a morphism is Parikh-collinear if and only if it maps all infinite words to words with bounded abelian complexity. So for example, if you take the binary Champernowne word, which contains all binary words, and mu the to-a-morse morphism, the abelian complexity function of mu of the Champernowne word will have a bounded abelian complexity function, and it's 2 if n is odd and 3 otherwise. Right, so this is a characterization of Parikh-collinear morphisms that we will see later on, or we develop later on the talk. And so what I plan to talk about are characterizations of Parikh-collinear morphisms, and we're going to talk about this with respect to binomial complexity functions, which I'll introduce in the next slides. Also discuss some automatic properties of fixed points of Parikh-collinear morphisms, and then further inspect what happens to binomial complexities when we start applying the two-or-more morphism to infinite words. And this is based on the joint work with Michel and Manon, as you can see on the slide. Now, just an important terminology observation is that in a word, a factor is a contiguous subsequence, while a subword or scattered subword is a subsequence. So, for example, in the word reappear, its length is 8. The number of letter occurrences of A is 2, as is the number of letter occurrences of E. And now for factors, you can see on the left, we have appear, app, and ear. But we also have subwords that do not appear as factors. So here we have ape, rap, and rear. So a factor is always a subword, but a subword is not always a factor. Okay, so now to binomial equivalence. We use this notation for the binomial coefficient of two words u and v. So this is just expressing the number of subword occurrences of v in u. As an example, you can find 101 in this word 6 times, and here are all the occurrences. And with this notion, we can define the so-called k binomial equivalence relation. So here we have a parameter k, and we fix k to be some integer, at least 1. And we say the two words are k binomial equivalent, so we're using this notation here. If the number of subword occurrences of x are equal for all x that have length at most k. As an example, we have these two words here that are two binomial equivalent. You can see it from this table that for words up to length 2, they have the same number of subword occurrences, but these two words are not three binomially equivalent because if you look at the subword 001, there are no occurrences in the word of the left, but there's one occurrence on the word of the right. Okay. So with this k binomial equivalence relation, we can define the k binomial complexity function, much like we did with the abelian complexity function. So here, instead of counting, again, all factors of length n of an infinite word, we count the number of k binomial equivalence classes we see among the factors of length x. Well, the first immediate observation is that if you have two words that are k plus 1 binomial equivalent, then they are k binomial equivalent. And from this observation, you can get a hierarchy of the binomial complexity functions. First thing to notice is that, in fact, the abelian complexity function is exactly the one binomial complexity function. But then we have this increasing chain that holds for all n, and we're always upper bounded by the factor complexity function at n. Here's a figure just to illustrate. So the blue graph here is the abelian complexity function. This would be the 2 binomial complexity function, and the green one, the 3 binomial complexity function. So what is known about binomial complexities? Well, here's an example. Of course, the two-amorphs word, which we all know and love. Just as a reminder, it's the fixed point of this morphism. Here's a prefix of it. And, well, this is completely known thanks to the work of Lejean, Leroy, and Rigaud. So here, if you fix any k, the k binomial complexity function will be essentially the factor complexity function for small lengths. And once you're long enough, it depends on how, if you're a multiple of 2 to the k, recall the k is fixed, then you have this value, while otherwise you'll get this value. And here in the graph, you can see how this behaves. The blue one here is the abelian complexity function. This will just alternate between 2 and 3. The yellow one is the two binomial complexity function, and you see these bumps at multiples of 4. It seems that the graph is a bit shifted, but anyway, it's almost a flat curve, but you have these bumps at every 4th position. Here's the 3 binomial complexity. The bumps are getting sparser and sparser, and 4 and 5. So anyway, this is what the complexity functions look like graphically. For Stormian words, recall that Stormian word is a infinite word for which the factor complexity function equals n+1 for each n. Of course, these are also those aperiodic words for which the binomial complexity function equals 2 for all n. And as an example, we have the Fibonacci word, which we also all know and love. So what is known about the binomial complexities? This immediately, so for the abelian complexity, it's just the constant 2. But if you look at 2 binomial or 3 binomial, you'll in fact get back the factor complexity function, which equals n+1 for all n. So this means that if you take any 2 factors in a Stormian word that are either they are equal or they are not 2 binomial equivalent. And well, this in fact characterizes Stormian words in the sense that if you take, you have an infinite word for which there exists some k such that the binomial complexity function equals n+1 for all n, then you are a Stormian word. Other binomial complexity functions that are known. So for the Fibonacci word, we also have this phenomenon where we get back the factor complexity function as soon as we're inspecting k binomial complexities with k at least 2. The same holds for billiard words. This is recently announced by Léo Bibion. For larger families of words, we have the Parikh constant morphic words. So these are, so Parikh-collinear morphisms, we require that the Parikh vectors of the images of letters are linearly dependent. Here with Parikh constant, we mean that in fact they are all equal. So here think of the two-amorphs morphism, for example. So if you look at a fixed point of a Parikh constant morphism, then you know that it's going to have bounded k binomial complexity functions where the bound will depend on the k that you're inspecting. Another family are generalized two-amorphs words, which would fall under this Parikh constant morphic words. The precise values of the 2 binomial complexities are known. It's a fairly recently published paper, but I think this was already on arXiv in 2021. And as a side note, we have a work in progress with Mehdi Golafshan and Michel here at Liège, where we are looking at all the complexity functions of the generalized two-amorphs words. Right. So I'm supposed to talk about characterizations of Parikh-collinear morphisms. Just recall that this is the theorem I mentioned earlier. The morphism is Parikh-collinear if and only if it maps all infinite words to words with bounded abelian complexity. And this is what we generalize. So here we have the following characterizations. So you have that a morphism F from A star to B star is Parikh-collinear if and only if you take any K and any two words that are K binomial equivalent, then their images are K plus 1 binomially equivalent. And the same holds if there just exists some K for which the same property holds. Oops, sorry. And the last two are more closer to the above theorem. So here, if you take any K, at least 0, then all words with bounded K binomial complexity are mapped to words with bounded K plus 1 binomial complexity. Here for K equals 0, it's understood that 0 binomial equivalence is just the equal length relation. So it's a trivial, fairly trivial equivalence relation. And the same also holds if you just find some K for which all words with bounded K binomial complexity are mapped to bounded K plus 1 complexity words. So about the proof, it's quite technical. I don't think there's anything, any deep insights. Doing a lot of computations. I mean, you can check it out. I think it's they're cute computations, but yeah, there's nothing more to say about that. But as a corollary of this theorem, we get a generalization of the Rigaud-Salimov result, where essentially what the corollary is that if you take a fixed point of a Parikh-collinear morphism, then it has bounded K binomial complexities for all K. And here again, the bound depends on K. And recall that the result of Michel and Pavel was talking about Parikh constant morphisms. So as an example, here's the graphs of the first three binomial complexity functions of fixed point of this morphism. Again, here the blue is the abelian complexity, the yellow is the 2 binomial, and 3 is the green is the 3 binomial complexity function. As you can see, the complexities can have rather strange initial behaviors, but they will kind of level off at some point. And yeah, while talking about this work in previous presentations, we got questions from Sportiello and Salo independently. They were looking at this particular graph, and they asked, is the abelian complexity function always ultimately periodic for fixed points of Parikh-collinears? Or more generally, is the K binomial complexity function always ultimately periodic? Well, this is not true. So here's an example of a Parikh-collinear fixed point, which does not seem to have periodic abelian complexity function. But how would you prove it? I mean, well, you can prove it straightforwardly for just inspecting the morphism. But what I'm going to talk about next is this automatic aspect of these Parikh-collinear fixed points. So we kind of wish to not work too much to get something like this abelian complexity function is aperiodic. So we do what mathematicians do is that we try to make some general observations of these words. And here, just as a reminder, what are automatic sequences? A sequence is k-automatic if and only if you can obtain it as a letter-to-letter coding of a fixed point of a k-uniform morphism. So k here is just a parameter. Another definition is that if you take any letter in the appearing in the alphabet, then the characteristic sequence of the positions of this letter A in your infinite word X is definable in the first order theory of the naturals with addition and this function Vk, which maps for n, it will give you the largest power of k that divides n. And a third definition is that there is a deterministic finite automaton with output such that when you feed in the base k representation of integer n, you will get the nth letter of your infinite word. And well, as an example, the Tuamos word is going to be defined with this automaton. So here you have your usual automaton behaves like an automaton. You have labels on the states, and when you put an input, say, for example, the base 2 representation of 3, you'll just follow the 1, 1. You get back to this state, and you're just going to spit out a 0. So this is how what we mean by this last definition. Okay, so now we're equipped with recalling what automatic sequences are. And well, if you have a Parikh-collinear fixed point, then it is actually k-automatic for k for this k. So essentially you're summing, you're taking the adjacency matrix and taking the trace of it. Okay, and this is well, this is already known since the late 70s. We only learned about it after getting reviews for our paper for words. But it's a fun construction. I will point out is that we're here are allowing erasing morphisms while it's unclear or it's not explicitly stated. Or it's explicitly stated that in these papers of Decking and Alouche that you're considering non-erasing morphisms, although the construction is straightforward for erasing ones as well. So here, just as an example, we have this this word which had the aperiodic looking abelian complexity. And in fact, we can generate it using this 5 uniform morphism and then use a coding to get it back. Okay, so we kind of wish to utilize this fact that it's automatic to get something about the abelian complexity function, right? So what we prove is that if you take the abelian complexity function of a Parikh-collinear fixed point, then it's actually k-automatic for the same k that the original, the fixed point is. And moreover, you can effectively generate this abelian complexity function. You can construct the DFAO, for example, that generates the abelian complexity function. And this is, as a remark, this is supporting Michel's conjecture that the abelian complexity function of a k-regular, a k-automatic sequence is k-regular. If you don't know what k-regular is, don't worry. This is just to point out that there is such a conjecture, and this is supporting it. What is known previously is that this holds for Parikh constant morphisms. This is due to the work of Guo, Liu, and Wen. And what's nice about this is that we can just query properties about abelian complexity functions using, for example, walnut. I think here I have the grammatical error that Jeff was talking about previously. Anyway, yeah, and that's exactly what we do. So using our constructions, we can construct this automaton that is generating the abelian complexity function for the word, and we can just ask walnut, is this sequence aperiodic, with a query that looks something like this, and it returns true. So it is aperiodic. So yeah, the original question perhaps was not that interesting itself, so just for this particular fixed point, but the method turned out to be quite interesting to how to prove such aperiodicity. So I'm going to go through a proof sketch of this theorem, stating that the abelian complexity function is going to be k-automatic. And the idea is following. So we have the fixed point of the morphism, which has the nice property that this is Parikh-collinear. But we also have the property that it's 5-automatic. So here we have these two factorizations. And we kind of really want to use this Parikh-collinear factorization to use this to define abelian complexity, because if you have a block that is a full factorization, you know that half of the letters will be ones and half of them will be 0, right? Because here 2 out of 4 are ones, here 3 out of 4 are 6 are ones, and so forth. While if you look at the factorization given by this 5-uniform morphism, you don't have these this nice property. The number of ones is going to differ between 2 and 3, it seems. So we wish to allow walnut access to this nice factorization, and here we define the notion of a cutting set. So here you have a pure morphic word x under the morphism A. So let's say we're iterating the morphism on the letter A, and we get this infinite word x. And here the cutting set is just the length and prefixes mapped under F. We just take the lengths. So for example, for the factorization in 1, the first few values in the cutting set are 0, 6, 10, 16, 22, and so forth. And the whole point about this is that this in fact is a k-automatic sequence. So we can show this for Parikh-collinear fixed points, that this is effectively definable in this theory for this particular k. And the proof goes through by, well, use an effective version of Moss's recognizability result. If you don't know what it is, don't worry. It essentially just says that you can locate the positions where the image of a letter begins in a factorization of an infinite word. And well, Moss's result is about primitive morphisms. So here, recall that we allow erasing morphisms. The reason why this works is that, well, the fixed point is, or the morphism is almost primitive. I'll leave it at that, but a generalization that tackles this problem is given by Béal, Durand, and Perrin in their forthcoming book. So we actually get to use an effectively computable constant coming from this recognizability result, which allows us to essentially recognize the cutting set. And well, as a corollary, we get that if we look at the sequence of integers of the pairs of the integer n and the number of occurrences of the letter a in the prefix of length n of an infinite word, there is a two-tape deterministic finite automaton that accepts these pairs. So in other words, this sequence is k-synchronized. I won't go to the definition any further, but this is essentially enough because we can now use a result of Jeff saying that the abelian complexity function will then be automatic. So yeah, I've brushed over a lot of details. I'll invite you to read the papers to see the interesting details of the proof. Okay, so that covers the part about automaticity. Next, I'll be talking about what happens to binomial complexities when we map an infinite word with the two morphism. So recall that the k binomial complexity functions are known exactly for the two-morph word. And now we're interested in words that have the same complexities up to some parameter k. So here, for example, if k is 3, a word has property p3 if the abelian complexity function is the same as the two amorphs words, the two binomial and the three binomial complexities are also the same as the two amorphs words that appear here. So here we're essentially assuming that the binomial complexity functions up to some parameter k look like the two amorphs ones. And what is interesting is that there's actually characterization of words that have this property p1. So assuming that you have that the abelian complexity function is the same as the two amorphs, they are those aperiodic infinite words that are essentially the image of another binary word under the two amorphs morphism. So we wish to extend this result to our binomial complexity functions. Here's a partial one direction that we can generalize of the previous theorem. It says that if you take any aperiodic binary word and you map it k times with the two amorphs morphism, then it will have this same binomial complexity functions as the two amorphs word. The first k binomial complexities are equal to the two amorphs words. And the proof is that we essentially extend results from the paper of Lejeune, Leroy, Rigaud on the paper computing the k binomial complexities of the two amorphs word. As an example, if you take the Fibonacci word and you map it 0 times with the two amorphs morphism, well, the theorem isn't saying anything. But if you map it once, you see that you will get the same abelian complexity. The theorem is not going to say anything about two binomial complexities. Now, if you map it twice with the two amorphs morphism, you see you'll get the abelian complexity is the same, and now the two binomial complexity is also the same. And the same for 3. So you can see that the two amorphs morphism is going to lose information about any binomial complexities depending on the number of times you apply apply it to a binary word. So that was a generalization of one direction of the theorem, and here's a partial converse. So for this, I just want to recall that an infinite word is called recurrent if each factor appears infinitely often in it. Right? So the partial converse is now saying that if you take a recurrent infinite binary word and you assume that it has this property pk, so meaning that the first k binomial complexity functions are the same as the two or more words, then X is essentially the kth image of a binary word under the two or more morphism for some aperiodic binary word. And we're currently working on replacing this recurrence assumption with aperiodicity assumption. So then we get the full generalization of Rishon, Sari, Zamboni result. So how do we go about proving something like this? Well, we use Rosy graphs and abelian Rosy graphs. So you have an infinite word X, and the Rosy graph of order n is the labeled directed graph where the vertices are essentially the factors of length n, and you have an edge between two vertices if there exists with the label AB, if there exists a word such that the start vertex is AW and the end vertex is WB, and you have that this word AWB is in the language. So this is a bit I suppose we should be a bit careful with the short lengths, but anyway, this is the main notion. So for example, in the Fibonacci word, you'll have 4 vertices, and the Rosy graph looks like this. And now what we do is we take the Rosy graph and we essentially identify all vertices that are abelian equivalent as 1, but we're going to keep all the labeled edges. So as an example here, these 3 vertices are all abelian equivalent. They'll be identified as 1, but we're going to keep the edges 0, 0. So this is this edge here. And we're going to keep the edge 1 labeled 1, 1. Right? And then we have a singleton abelian equivalence class here. So this is just mapped to this vertex. And we're just keeping the same labels there. Okay, so with these abelian Rosy graphs, they behave very nicely with the two morphism and I suppose any Parikh constant morphism. But in any case, so if you look at the two-morph word, these are what the abelian Rosy graphs look like. So for even lengths, you'll have this kind of a graph with 3 vertices. Recall that for even lengths, the abelian complexity of the two-morphs is 3. And you'll have these relations. This is regardless of you're assuming that m is at least 1. And for odd lengths, you'll have 2 abelian equivalence classes. So the abelian Rosy graphs will look, they'll have 2 vertices, and the transitions will always look like this. And yeah, so we start analyzing the behavior of mapping a word with a two-morph morphism by understanding the abelian Rosy graphs. So here we're going to put an equivalence relation or two equivalence relations on the edges of the abelian-Rossi graph. And essentially, okay, this is a technical definition, but what the first equivalence relation is that we're going to identify all the edges that have the same start vertex. So here, for the blue ones, they start from the center vertex labeled M. And the second component of the label has to be equal as well. So here, the second component for both these edges is 0. So we're going to identify these two edges. And the same for the brown edges here. Again, they have the same start vertex, and the second component is 1 in both of these edges. So they are counted as the same. The red and green edges are singletons under this equivalence relation. So this is the first equivalence relation. The second one is illustrated here. So here we just want that the end vertex of an edge is the same, and the first component of the label, they should be equal. So again, the blue edges here both end in this vertex, and they begin, the label's first components are both 0. So we have two equivalence relations. Essentially, what we're going to do is we're going to count the number of these equivalence classes that we can see in an abelian-Rossi graph. It's essentially this here. And why do we do that? Well, this is a very technical proposition, but this essentially allows us to understand the k+1 binomial complexity function of an infinite word x that is the kth image of under the two-or-more morphism. So essentially, I don't want you to read this very carefully. The point is that here, when we're getting a formula for counting the k+1 complexity of x, we can see we're counting the number of edges appearing in the abelian-Rossi graph of y. Here's the abelian complexity function. So this is the number of vertices in the abelian-Rossi graph. And here in the second formula, we're also counting the number of these equivalence classes we placed on the abelian-Rossi graphs. It's yeah, so this is a technical formula, but in any case, this allows us to compute k+1 binomial complexities from the abelian-Rossi graph of y. And now, just to recall, what are we proving? We have a recurrent word, and we're assuming that it has the first k binomial complexity functions are equal to those of the two-or-more word. Then x should be the kth image of a binary word under the two-or-more morphism. The quick proof sketch is that the base case, we proceed by induction, the base case is this result of Grisham, Sari, and Zamboni. And then inductively, if you have a word that has property k+1, then it will have property pk, and thus it has to essentially be the kth image of the word. And what we show is that this word y appearing inside as the argument actually is the image of a binary word under the two-or-more morphism. And what we do is we look at the possible abelian-Rossi graphs of this word y and use the formula that we derived in the previous slide. So yeah, I suppose the point here is that we made use of these abelian-Rossi graphs in a fun way. I forgot to mention that the abelian-Rossi graphs were essentially appeared in the work of Grisham, Sari, and Zamboni. They don't think they made very much use of it. But here, for the two-amorph morphism, it worked out quite nicely. It's behaving quite nicely for what we want, right? Okay, so how much time do I have? 10 minutes. Okay, so I will go on to the next topic. So this is kind of explaining why were we interested in the complexity functions of a word after applying the two-amorph morphism several times. So if you recall that for the binomial complexities, we have this this chain of inequalities between the consecutive complexity binomial complexity functions. And it was proposed, or we have a question that was inspired by a question in Lejeun's PhD thesis, and for this we need a bit of notation. So here, let's take two functions from the naturals to naturals, and we write f is smaller than g whenever f is always bounded by g for all n, and for infinitely many n, we have a strict inequality. And Lejeun's question essentially was that does there exist an infinite word for which you have this relation for all k? And well, of course, we have trivial answers like the two-amorph morphism will have this property, and so will the Champern noun word on the appropriate, or take the binary Champern noun word, you will have this property holding as well. But well, Lejeune really wanted a word for which the abelian complexity is already unbounded. So the two-amorph word is not applicable to her question. And the Champern noun word is, well, you just have all words, so you have no structure. So what we proposed is that let's have more structured answers to this question. So here we have a word for which this will hold. So the binomial complexity functions will always obey this this relation that let's say the abelian complexity function is always bounded by the two binomial complexity function, and for infinitely many n, there is a strict inequality. And here, well, this is a morphic word that we made for this particular answer. And the point is that essentially we're going to build the two-amorph morphism into the word as a substructure, and just to make the abelian complexity function to be unbounded, we'll just have essentially arbitrarily long runs of ones after this this coding, where tau essentially we're going to keep the two-amorph word as a substructure, and we're going to have these arbitrary long ones, blocks of one appearing. This will have unbounded abelian complexity function, and because we have two-amorphs as a sub structure, we'll also have this relation between consecutive complexity functions. Another answer here is the Grillen-Berger construction. Essentially, what it gives is that you'll have unbounded abelian complexity function. It's a binary word and uniformly recurrent. So it has it has stronger properties, but in any case, this is also uniformly recurrent, which this word is not. And here, a uniformly recurrent, I mean, each factor occurs infinitely many times within bounded gaps. Another question we were thought about, inspired by Lejeune's thesis, is that, okay, let's fix some k, and does there exist a word for this k such that the first k binomial complexity functions are really different, but then this collapses to the factor complexity function at the k binomial complexity? And for this, we use this two-Amorphs observations that we made. So here, this infinite word, if you take the kth image under the two-Amorphs morphism, should be a mu, then it will have the same first k binomial complexity functions as the two-Amorphs morphism. So in fact, I mean, we'll trivially have this. And we can also show that these will actually have to differ, the k and k plus 1. So the question is, can we now make this k plus 1 complexity collapse to the or the k plus 2 complexity collapse to the factor complexity function? And indeed we can. So here, if we take any Sturmian word and we map it with the two-Amorphs morphism k times, then we will have this chain. And this is essentially the answer to that question posed previously. And as a proof sketch, well, as I mentioned, we will always have this chain. So the question is, can we first show that this is not the factor complexity function at k plus 1, but then at k plus 2, we get the factor complexity? For the first one, we can again start analyzing abelian-Rossi graphs, and we essentially determine the abelian-Rossi graphs of Sturmian words, and we show that this is not equal to the factor complexity function. But if we now look at the k plus 2 complexity function of this kth image of a Sturmian word, then we can show it's the factor complexity function by using the fact that if you take any words in any two factors of a Sturmian word that are two binomially equivalent, then they actually have to be equal. Again, yeah, I'll invite you to read the details from the paper. But yeah, this was the whole point of why we were interested in complexity functions of words of this form. So just as a final example, to illustrate the theorem, here we take the Sturmian word. If we apply the two-Amorphs morphism 0 times, then, well, we'll have that the abelian complexity function is 2, and the two binomial complexity function collapses to the factor complexity function. Here we have, if we map the Sturmian word once with the two-Amorphs morphism, then, well, we know that we'll have the same abelian complexity. The two binomial complexity is, well, I didn't say what it is, but essentially it's going to be this constant for each k. But the point here is now that the three binomial complexity function equals the factor complexity function of this word, and so forth. Okay, so I'm going to wrap up now. So what did we do? We considered Parikh-collinear morphisms, and especially with respect to binomial complexity functions. So we gave several characterizations of Parikh-collinear morphisms using the binomial equivalence relation and binomial complexities, discussed automatic properties of Parikh-collinear fixed points, and applications of the two-Amorphs to binary words. Now, what we might want to do in the future is we want to, as I mentioned previously, want to complete the full generalization of the theorem of Grisham, Sari, and Zamboni. We're also inspecting the binomial complexities of other families of words. I briefly mentioned some known results. An interesting aspect that I did touch upon in this talk is the possible behavior, different behaviors between consecutive binomial complexities. So here we had these chains which collapse to the factor complexity, but maybe more of the flavor of how much can the complexities differ. Can you go from constant to full complexity, for example? Another point which should be doable is that, okay, I talked about automatic abelian complexities of Parikh-collinear fixed points, and this should also hold true for any binomial complexity of a Parikh-collinear fixed point. Yeah, this is what we plan on doing sometime in the future. And one other thing that is interesting, so in the proof we use the automaticity of the cutting sets. So here we were essentially relying heavily on this recognizability result on well, essentially primitive morphisms, but you can imagine cases where you have no hope of having any recognizability constants, for example, but still, if your morphic word happens to be too automatic with a strange morphism, you still can define this cutting set in the suitable theory. So this is, let's say, a very broad question, and this is something that came up in recent discussions, and this could be interesting to see what happens with these words. And with that, yeah, thank you very much, and happy to answer any questions.
Thanks a lot, Markus. Does anyone have any questions? Jeff?
Yeah, hi. Very nice talk. Thanks so much.
Thank you.
Just was wondering if you could say a little bit more about the Grillenberger construction.
This one here. So the point of the Grillenberger construction is that you wanted to have uniformly recurrent words for an arbitrary with an arbitrary entropy. So this is just one particular, what we proposed here is just one particular word of the family of words. And the construction essentially is, in fact, this construction here is taken from the chapter of factor complexities in the Combinatorics Automata Number Theory book by Cassagne and Nicolas, I think.
This one?
Yes, it must be there, chapter 4.
Okay.
If I remember correctly. But there's a recursive definition. It's a very general construction. So again, you want to construct a word with some prescribed entropy and with some several sequences of integers. You can construct this, and we took one particular sequence.
Okay, thanks.
Thank you.
Anyone else have a question? No, if not, thank you very much, Markus.